If you've ever done differential scanning calorimetry, it's DSC, it's striking how the freezing point is usually much lower than the melting point. Now, at first glance, that's puzzling. If we draw a phase diagram, you see that we go back and forth across this line between solid and liquid. Their freezing point and melting point should be exactly the same temperature. And so the equilibrium, freezing point, and melting point are the same unless there's some other effect. So what's the other effect? Well, the other effect would be if we tried to freeze something without having a solid surface to nucleate onto. So let's draw two pictures. Let's imagine that we have a sample cell and we've got some liquid and then we have some solid at the bottom. So we've got solid and liquid and they're in equilibrium. If we remove some heat from this sample cell, we expect that more solid will form. And if we add some heat, we expect that more liquid will form. And both of those processes will happen exactly at the normal melting point or freezing point of the compound. However, let's look at a totally different situation where we have our liquid and imagine that maybe this is water and these are hydrophobic surfaces. So the water is not going to stick to these surfaces. So that means when we freeze, we have to form little crystals of solid. We have to nucleate. And so those particles are small, they have a lot of surface area, and we know it costs us energy to make surface area. An alternate way of looking at this is that because of the very small radius of curvature, there's going to be a lot of Laplace pressure inside those initial solid particles that we make. And that's going to increase the chemical potential of the material in the solid, and that's going to disfavor the solid phase. So it's going to be harder to freeze when we have to nucleate. In the first example, we didn't have to nucleate because we already had a pre-existing solid that we could freeze onto. So we expect here just to melt at the regular melting point or freeze at the regular melting point. Here, the freezing temperature should be actually lower than the melting temperature, and we call this supercooling. So this is what happens when we try to freeze without having any kind of anything to nucleate onto. And this will happen if we try to freeze any liquid in a really clean vessel that doesn't have any sharp edges or anything that can act as a nucleation site on it. So let's look at the thermodynamics of freezing when we have to form these small particles. And we're going to make a few approximations. Normally particles form crystals that have different crystal faces and different crystal edges, different surface energies. We're going to just assume that the particles are totally isotropic, so we can just use one number for the surface energy, and for simplicity, we'll make spherical particles. All right, let's look at these two scenarios. So in the first one, we just have something melting at its regular melting point, where solid and liquid at equilibrium. So we can say the chemical potential of the solid, and this is going to be at the regular melting point, is equal to the chemical potential of the liquid, also at the regular melting point. That's pretty simple. Okay, what about over here? Over here, we have the chemical potential of the liquid, and the liquid is at some new melting point. We'll call it Tm prime, and it's in equilibrium with the solid, which is also at Tm prime, and it is also at a new pressure, so we'll call it at P2. So if we want to relate these two potentials together, we're going to have to figure out how chemical potential is affected by temperature and by pressure. So we go back to the molar Gibbs function. So we say the differential of the chemical potential is minus S bar dt plus V bar dt dP. And then we say, what are we doing? Well, to both the phases, we're changing the temperatures to the new melting temperature, the one where we're supercooling. And for the solid only, we're changing the pressure. So notice the Laplace pressure is only exerted on the interior face. We're not changing the pressure here at all. Okay, so for the liquid, we can say that we've got the chemical potential at the original melting temperature, plus we have to integrate this term. So we've got the negative of the molar entropy of liquid, and we're going to integrate temperature from the temperature we started at, Tm, to Tm prime. But we also, well actually that's all we're doing to the liquid, is just changing the temperature. For the solid, we can relate the chemical potential under the new situation to the chemical potential in the original situation. What have we done? We've changed both of these. So we need an integral to get to both of these new points. So we're going to, first of all, integrate to get from Tm to Tm prime. So that's minus the molar entropy of this case of the solid. And then we have to get to this new pressure. So we integrate from our original pressure, let's call it P0, to P2. And that is going to be the molar volume of the solid dP. And so what we're doing here is saying this is equal to this, and this is equal to this. So we have our original index conditions, and then if we integrate, we can get to the new conditions that we have over here. And the reason we do this is that once we've written this, we recognize that this chemical potential and this chemical potential we know are equal from what we saw in the original situation. So that allows us to cross these out, cancel them, and so now we can do the integrals. So first what we'll do is we'll gather the entropies on the left-hand side. So we've got the entropy of the liquid minus the molar entropy of the solid, dt. And on the right-hand side, we have the molar volume of the solid. Okay. And looking at these integrals, if we assume that the molar entropy of the liquid and solid don't change that much over the temperature range of interest, we can recognize, wait a minute, this is just molar entropy of liquid minus solid. That's the delta S of fusion. And this is going to be just a constant, so we can pull it outside the integral. So we can rewrite this as the integral of delta S of fusion dt going from Tm to Tm prime is equal to, and let's go ahead and pull out we know the molar volume of the solid is not going to change appreciably as we go from P1 to P2. Or I guess we were calling it P0 to P2. We've got to remember that negative sign there. So at this point, we can pull the molar volume out. We can pull out the delta S of fusion if we assume that doesn't change much over the course of the temperature change. So we have Tm prime minus Tm is equal to the molar volume of solid. And we can this is just delta P. And what we'll do is we will move this negative sign over to the other side. and then plug in our expression for the change in pressure. We know the change in pressure is just the Laplace pressure, so it's 2 gamma over r, assuming, of course, that we're doing spherical particles. And then we can just solve for Tm prime. So Tm prime is equal to the original melting temperature minus 2 gamma times the molar volume of the solid all over the radius of the spherical particles. And we also have to divide by the delta S of fusion. And if we wanted to, we could rewrite this as in terms of the enthalpy of fusion, just by substituting that. So we can say 2 gamma molar volume of solid, radius of the particles, and just substitute the delta S of delta H of fusion divided by the T. So we have to put in a Tm here as well. And this is our final version of the Gibbs-Thomson equation. And the Gibbs-Thomson equation allows us to see how much supercooling we can get for a given particle size.